Okay, welcome back, everyone. I remind you that next week we don't have class because of Shavuot, so you'll have a chance to maybe catch up a bit on the homeworks. Also, if anyone is affected in any way by the current security situation in Jerusalem or in the South, and that impacts your ability to complete the homework in time, tell me or Yehu, and we can arrange for an extension on the deadline so that you can be safe until this thing is hopefully very soon over. Today we move on in our discussion about stars and identifying stellar phenomena, and we're going to break some of the assumptions or mildly deviate from some of the assumptions that we've made about stars being completely perfect, symmetric, and stationary. And we'll talk about variable stars, types of stars which appear to be changing in luminosity, profile, temperature, and other parameters with time. So you can't just put them in maybe one exact fixed position on an HR diagram, or maybe if you can look more deeply into the spectrum, you find that they are actually changing from time to time and are not fixed. And we're going to distinguish between 4 different levels of variable stars. The first one will be stars that are not considered variable stars, like our sun, but we'll see how every star is actually slightly variable. Nothing is completely symmetric, either spherically or with respect to time translation. So things change in time and in space. We're going to talk about what are considered intrinsic variable stars. Those are stars whose luminosity and physical properties change due to some internal mechanism. Something in the star changes, therefore we see it differently as time goes on. And we distinguish those from extrinsic variables, which are themselves fixed or more or less fixed, but they can have an effect on each other through a double system, typically binary systems, which will cause their luminosity to experience these stereotypical dips or dimmings periodically with eclipses or with other effects that the stars have on each other. So those will be extrinsic variables, and outside effect causes them to appear to vary. And we'll finish with cataclysmic variables. Those are stars who undergo in a system which causes them to undergo such an extreme change that it's cataclysmic. It can actually cause an explosion, an eruption, something very dramatic and drastic, which changes with time. So we'll start with our own sun. I see there's a question. No Dyson spheres at this point. We'll talk about energy output and different scales of energy later on in the semester. But now we're just dealing still with individual star or star systems and their electromagnetic output without any that we can detect today. So we're still talking about common modern day observations. So our sun is a typical main sequence star, as we characterized it before, based on color and luminosity. It's a G2V star. I remind you that G refers to the color. 2 means it's slightly to the right on the HR diagram of the beginning of the G stars. The V means it's a dwarf or a main sequence star. That's the branch of the HR diagram classification. And although it is pretty much stationary through time, it is not completely stationary through time. It's not completely static, as the images on the right can show in the optical and in UV. We see that the star is very, very non-stationary. The first thing that we can, and non-symmetric, or at least we can see that there's texture and there are changes going on, and we'll discuss some of those. The first of them is that the sun rotates. It rotates around its own axis. It's not just a fixed zero angular momentum star. It rotates around its axis, and it has a period on average of 28 days, so very close to an Earth month. But unlike the Earth, which rotates as a rigid body, so every point on the Earth has the same duration of the day, of 24 hours, more or less, the sun is a ball of gas. And so it's not rigidly held together. It's not restricted to only have the same rotation rate all across the sun. So the poles actually rotate slower than the equator. The equator completes a revolution in 25 days. The poles complete a revolution in 33 days. It's not only an angular separation based on the latitude in the sun, it's also a function of depth into the sun. That is what we can measure most easily from the outside here at radius of 1, so the external part of the sun. We can see the rotation changing by latitude. Here the vertical axis gives us the period of rotation or the frequency of rotation in nanohertz. And so we see that it is maximal at the equator, minimal towards the poles, but that's only at the surface. If we look further into the sun, we see that these kind of differential rotation, the rotations period changing with latitude, is also carried out pretty much almost halfway into the sun radially. But the core, the inner part of the sun, does rotate more rigidly. So there's some velocity or angular velocity, frequency of rotation, which characterizes the center of the sun almost regardless of latitude. And then we have this divergence or this separation, this bifurcations going outwards towards the surface. This is related or can help create and induce a envelope or a sphere of a spherical shell just in between the part which rigidly rotates and the outside, which rotates at different velocities, where we have a solid core or almost rigid core, not solid but rigid, rotating as one, and then separation of different velocities at different latitudes. So this separating region is called the tacho line, and is important for convection currents and for magnetic fields and for many other phenomena which are related to the differential rotation of the sun, or the move from rigid rotation to differential rotation. So that's regarding the angular part, the rotation of the sun. As we know from the stellar surface, it's also not spherically symmetric. We have granularity. We have this texture of cells, which, as we saw maybe a week or two ago, can be quite big. They can appear the size of a large country on Earth. And they're related to convection going on in the outer part of the sun and convection cells. So again, the sun is not static. Things are definitely moving, and we can see that they're also causing a texture to appear. The sun is not smooth in that sense. Beyond those low granularity features, we can also detect various types of acoustic waves or oscillations in the sun. So the sun is also not stationary in time, and we can measure through a field which is called helioseismology, kind of like seismology on Earth, but referring to the sun, helioseismology. And we can detect these waves propagating through the sun. We distinguish between different types of modes which can propagate or exist in the sun. The most easy ones to follow on the outside are pressure waves, or P modes, which are driven by the pressure pushing back on perturbations, causing waves. The next type is gravity or G modes, which are basically buoyancy waves. These are caused by in the regions which are stable to convection, where matter can, if you have a perturbation, a disturbance, matter flows up, gravity will push it back down. Or if you have less buoyant material, it will be pushed back to its origin, but this can have some frequency and it can produce these oscillating modes. And these are gravity-driven modes, so they're called G modes. They're more common, more internally in the sun. And we also have surface tension gravity modes called F modes. These are very similar to waves on the surface of a fluid on the Earth, like waves at the ocean, where the surface tension and the gravity interplay to create waves traveling across. So these are the different types that we would like to measure. And this helioseismology is actually one of the main tools that we have to probe into the sun and see things that are not just restricted to the surface, as you've heard in the previous lectures and tutorials, and now are working through in the homework exercise. Opacity to electromagnetic radiation makes it hard to look deep into the sun, but helioseismology can, in some sense, complement our information and tell us what happens below the surface through the waves that we can measure from the surface or from the outside. Non-electromagnetic waves, these are different types of pressure, gravity, buoyancy, other types of pressure and density waves that we can detect on the outside. These can happen on a quite fast time scale, and we'll see the calculation of the velocity of sound waves, basically, in the sun a little later, acoustic oscillations. But as we mentioned last week about evolution of stars, there are also gradual long-term changes in the sun, which have to do with the composition of the stellar core. Because the sun is constantly burning hydrogen into helium, the amount of hydrogen is constantly decreasing, the amount of helium is increasing, which means the chemical composition, or if you want the average molar atomic mass per particle mu, changes in the core. This comes in through the equation of state and the relation between pressure and density to gradually change the equations in the center of the sun, in the core of the sun. And this has an effect in itself on the luminosity, which means the luminosity of the sun today is not what it was when the sun first began its life as a main sequence star, as a zero-age main sequence star. It is now about 30% higher in luminosity than it was about 4 or 5 billion years ago. And it's still changing very gradually. It increases by about 1% every 100 million years. So not an effect we expect to notice in our own lifetime, but when we discuss the evolution of our solar system and life on Earth and long duration processes, we have to remember that the sun is and still does change its luminosity on a very, very long time scale. Any questions so far? Okay. A minor point which is worth keeping in mind about calculations regarding acoustic waves and sound waves in any medium, in particular in our sun, is how these waves are created and how they are propagated. And the way to calculate this is if we slightly allow ourselves to digress from hydrostatic perfect equilibrium. So we're going to do basically a perturbation expansion about hydrostatic equilibrium. We're going to be almost at equilibrium. But if we make a small modification in density or pressure, for example, if the pressure rises slightly in a particular point, it's not going to explode the star. It's not going to be a runaway process, but it might cause the process, but it might spread elsewhere. That is, the environment will reduce the pressure in that point which changed back to the ambient pressure, but that will have a ripple effect or a wave effect propagating outwards. And those are typical sound waves, which are similar to the ones that we know here on Earth. And similarly, we can calculate the velocity at which they propagate and see that the velocity depends on the pressure and the density. And so how do we calculate it? We break hydrostatic equilibrium, but we only do so to a very small degree. So locally or semi-locally, we'll say that dV dt is no longer zero. It's no longer completely static. But if there's a pressure gradient, that pressure gradient can induce some velocity. Basically, you can think of this equation as Newton's second law, ma equals F per unit area in this case. So instead of mass, we're going to have mass density. So okay, per unit volume. So we're going to have here acceleration times mass per unit volume. And on the right-hand side, we're going to have the gradient of the pressure. If you consider this tube here on the right as kind of a model for what we're looking at, then the mass inside is the volume L times A surface area or cross-section area times length L times rho, the average density in this little tube. The force will be the difference between the pressure on the right and the pressure on the left. So we can think of it as P right minus P left, or at the limit where it's very small, dP dx, the gradient of the pressure times the length L. That's the gradient of the pressure per unit area, because pressure is force per unit area. If we multiply then by A, then we have force per unit mass again, dP dx between the right side and the left side, equal to basically ma, or divided by volume, rho dV dt. So this equation here is just an example or a simple case of Newton's law, second law, where the force comes from pressure or pressure gradient. The change in pressure creates an acceleration. However, we can't just have random accelerations or large accelerations, because matter doesn't fly out of the star. The star is still almost in equilibrium. And when we look at this regime where we are very near equilibrium, what we can say is that whatever mass comes into this tube from the right, from the left, has to equal the mass leaving the tube on the right. So velocity can change from place to place, and density can change from place to place, and pressure can change from place to place. All of these V rho and P on the right here are dependent on position in this one-dimensional case. But the flux has to be conserved, the flow or the mass flux, because through this tube, we can't have net mass moving to the right or to the left. What this means is that the flux of the flow of mass, this J, which is equal to rho times V, the velocity times density, is a constant. Which means in differential form, I can make the derivative of both sides. The derivative of a constant is 0. The derivative of rho times V is the product, rho dV plus V d rho. And get this equation here, rho dV equals minus V d rho, just from this simple condition of conservation of flux or of flow. So I don't have any matter accumulating anywhere. It just flows around. These two equations are enough to give us a first order estimate of the velocity of sound of these waves. How do we do that? We see that on the left-hand side of the top equation, we have rho dV by dt. But we can replace rho dV with minus V d rho. You can think of it as integration by parts or the Leibniz rule or any other transformation which simply comes from conservation of flux. And so now we have minus V d rho dt on the left is the force per unit mass minus dP dx, the gradient of the pressure. Another thing we can do here is notice that we have dx on the right and dt on the left. So we can multiply by dx, or if you want, use the chain rule to change the derivative with respect to t with the derivative with respect to x, d rho dx, and then multiply by dx dt. In any case, what we get here on the left is this dx to dt term, which itself is just another another way to say V. So we actually have V squared on the left, and this d rho we can move to the right side. So we, again, think of it as changing the variable for differentiation, the chain rule from calculus, and we have dp d rho on the right-hand side. So we see that the velocity squared, the velocity of these waves propagating and bringing extra matter and increasing the pressure locally, the velocity is actually related to the pressure and the density. Actually, it's the derivative of the pressure with respect to the density. And so we can find directly that the speed of sound v is square root of dp to d rho. The dependence of the pressure on the density, which comes from the equation of state of whatever matter we're talking about, is exactly what will give us the velocity of the sound. If you take a simple case of a polytropic equation of state, then you know that there's just a power law, gamma, an adiabatic index relating rho and p. And so the derivative of p with respect to rho will bring us a gamma prefactor and give us rho to the gamma minus 1. Was that my computer or some of your computers? Let me just, okay, close that off. Okay. Okay, so we have a gamma prefactor, rho to the power of gamma minus 1, divided by the removal of one derivative. And so again, we see that taking the derivative is equivalent to a prefactor gamma and to just the division by rho instead of division instead of a differential. So in this simple polytropic case, we don't even need to use the full equation of state. The prefactor alpha factors out or cancels out. And we have a calculation of the speed of sound in a medium given directly by the pressure, the density, and whichever polytropic index we have. You can do this for your favorite materials, air, water, different temperatures and different densities. And you can do this for the sun. And then if we can measure the velocity of sound waves propagating in the sun, we can use them to infer the pressure and the density. And this is how we can probe into the sun. Questions so far?
You say we can use it to measure the density and the pressure in the sun, but how do we measure those sound waves if you can't, I mean, in the space between us and the sun, there is a vacuum. How can we measure those sound waves if they're passing through 8-minute light minutes of vacuum?
So obviously we don't measure the sound waves on Earth because there's no material in between. Rho is 0 and you don't have sound waves propagating in vacuum, unlike electromagnetic radiation. But you can follow the stellar surface and you can see perturbations of different spherical modes and see what their frequencies and amplitudes are. And of course, frequency is related to the speed of sound, and you have the wavelength, the frequency, and the speed of sound basically related by lambda equals ct. So if t is the period of a wave, c is the velocity, in this case v, and lambda will give you the wavelength. Then just by looking at the sun, you can trace, looking from the outside, you can trace perturbations on the surface of the sun or close to the surface of the sun, and infer what the velocity was of those waves, and use that to probe internally inwards. Very similar to how seismographs work on Earth in some sense. You can probe a lot of geology about the construction of the Earth below the surface by measuring propagation of sound waves on the surface of the Earth. So they propagate through the depth of the Earth, but you can calculate and measure the effect they have on the surface and use that to infer what happens down below.
Okay. Thank you.
Okay. Another effect that we can easily see from the Earth but is related to the non-stationarity of the sun and to its internal workings, are sunspots, which I'm sure you've heard of. We mentioned them before in this course. We mentioned Galileo as the first one in the West to see them with a telescope. Well, that wasn't entirely accurate. There were periods of very heightened activity of solar sunspots, solar activity. And in some of those periods of heightened activity, they could be seen with the naked eye, even before the telescope. And they were in fact seen and documented over 1,000 years, even about 1,600 years before the invention of the telescope and its use for astronomy. So we know from Han Dynasty records in China, the year 28 BCE, we already have records of sunspots. So we know that they were followed as part of what the Chinese were doing in astronomy back then. They recorded them in imperial records. They were considered important enough that the sun was becoming darker or has spots on it. It was noted as an exceptional event. We had Korean records, which we still have, detailing the particularly intensive sunspot activity of the winter of 1128. And from the same winter, we also have records from England. John of Worcester drew this kind of schematic. Obviously, it's not very accurate. He didn't have a telescope. He just did this by eye. But he did mention that there were these dark spots appearing on the sun. And we have these records to this day. So we know that when they were exceptionally dark or intense, they were noted. And people saw them even without a telescope. Obviously, since the invention of the telescope, it became much, much easier. And was almost simultaneously seen by multiple observers in England, in Frisia, which is today around Germany, Netherlands coast, in Bavaria, and of course from Italy by Galileo Galilei himself. And we have here different records of observations. Here, Harriot's notebook from England in December 1610. We have Galileo's records on the right. We see that he actually followed them from day to day and saw that they move, they change their shape and position. They themselves are not stationary. And we have Christoph Scheiner's book describing the sun from 1630, following them for a very long time and following the motion of sunspots on the sun, so darker patches on the sun. Today, we know that these sunspots, we've been following them for now over 400 years, as you can see on the bottom. And we know that their intensity and their breadth, the amount of sunspots and the area that they cover from the stellar surface, the solar surface, actually changes with time, and it changes with a period of about 11 years, called the 11-year solar cycle. During periods of more intense sunspots, so when more of the sun is covered or darker, or appears to us to be darker, it actually indicates an increase of luminosity. There's an increase of about 100 times more, 100-fold increase in UV and X-ray. That's balanced by lower luminosity in other parts of the spectrum. So to us, it looks darker, but actually it's a lot brighter in UV and X-ray. Combined or integrated over the entire spectrum, it's about a factor of 0.1% of total luminosity in the change. So it changes the profile. It gives out off a lot more UV and X-ray than parts which are not covered in sunspots, but the overall luminosity only changes by a little, because of course, most of the sun's output is not in UV and X-ray, it's in the visible band. Here we see examples of 2 points in the cycle, solar minimum. We see that the sun is almost smooth, or looks to be almost smooth in the optical, as opposed to a solar maximum, where we see that a lot of the sun, in relative terms, is covered in these dark patches of sunspots. On the right here, on the bottom, we have an example of one cycle, I think this is 2 cycles ago, in ultraviolet. We see from the beginning that the sun is almost smooth. Slowly, the number and area of these sunspots, which again are darker in optical but brighter in UV, grows until about 5.5 years later, half the period, we see that a lot of the sun is covered in these brighter UV patches, in these sunspots, and decrease again down to the next solar minimum, which will begin the next cycle. And we know that these cycles themselves do not just repeat themselves. There's also a variation between cycle to cycle. And in the 400 years that we've been following them and documenting them with telescopes, we now have kind of this view presented here on the left of repeating cycles every 11 years, but the cycles themselves have modulations and effects behind them, which we actually don't fully understand today. Of particular interest is what's called the Mondo Minimum. Shortly after sunspots were discovered, they disappeared for about 50 years or almost disappeared. And this can happen, we think this can happen more times, and we don't exactly know what effect this will have on the sun and on climate on the Earth. This is obviously one of the things that we study when in solar physics, studying what drives these variations in solar cycles. We have less accurate data, which we can use to look further back. If we look at tree rings we can trace for about 11,000 years, which is about 2 times the half-life of carbon-14, the isotope we typically use for carbon dating organic material. And we can use tree rings to kind of try to study through that period what were the conditions of radiation arriving at the Earth. So we can infer sunspots in that way as well. Okay. Today we understand and have for about 100 years that these sunspots are strongly related to magnetic phenomena. So the sun has convection flows, as we mentioned multiple times before, due to its heat distribution, its heat transfer mechanisms, and also due to the tacho line, which distinguishes between the rigidly rotating core and the outside. So we have this differential rotation, which can also induce magnetic fields and sustain magnetic fields. And this magnetic activity is related to sunspots. How do we know that? We can directly measure the intensity of a magnetic field anywhere that we want to look at by examining the spectrum. This is using the Zeeman effect, which you might have heard of in quantum mechanics or in Introduction to Modern Physics. Where there is no magnetic field, spectral lines will basically be the same. Transitions, or a single transition of an electron from one level to another level will have a typical energy gap, hence a typical frequency for photons coming out of that. But if there's a magnetic field, it breaks the degeneracy between electrons at the same N and L quantum numbers based on their different M quantum numbers. So the component of their angular momentum aligned or anti-aligned with the magnetic field. So for example, for L equals 1, we can have 3 different M values, -1, 0, or +1. And so we'll have a split in the line around this average based on the intensity of the magnetic field. And this is what we see here. We have a 3-way splitting of an L equals 1, but different types of M orbitals. And when we point our telescopes or our spectrographs into a region with intense sunspots relative to areas where there are no sunspots, we see this difference in the spectrum. And so we can measure the intensity of the magnetic field in the sunspot, and we know that they're directly related. Sunspots are basically connected to or caused by magnetic regions of intense magnetic fields. Today, we can also follow not just the intensity of the magnetic field, but also the polarity in the direction of the magnetic field. And doing that, we find that the period of sunspots solar activity is actually not 11 years, it's 22 years, because every 11 years, the intensity completes a cycle, but the polarity flips. So we have actually 2 flips for a full cycle, and we can see this here on the right. Now with imaging the intensity, position, and area of sunspots, we can see that they basically travel from a high latitude of about 30 down to the equator, flip in polarity, continue off to the other side, and repeat in that way. So we have polarity switching and intensity switching. And of course, if you only look at the amplitude of a wave, then, or the wave squared, you'll basically double the frequency or half the cycle, because you're only looking at the absolute value and not on the sign. But now we know that the period is actually 22 years, approximately, and we can follow the sunspots through their magnetic effects along this cycle. Any questions?
Yeah, so the sunspots come from the Zeeman effect?
The sunspots don't come from the Zeeman effect. The Zeeman effect affects the spectrum. It means that if we take a spectrograph and put it on our telescope, and we point the telescope to a region with a sunspot or a region without a sunspot, then in the region without a sunspot, we will get single thick spectral lines. Because there's basically the energy of electrons there is independent on their m quantum number. It only depends on n, how far they are from the nucleus, basically.
Okay.
But if you then point the same telescope to within a sunspot, you'll see that the spectral line splits. And it splits because now the energy of each electron depends not only on its n quantum number, it also depends on its m quantum number via the coupling Lz dot b. So the angular momentum of the electron in the z direction dot the magnetic field in the z direction, or L dot b basically. So Lz bz if we call the direction z. And that value can be plus, minus, or 0, right, in quanta of h bar times the strength of the field B. And so now we have that an electron, for example, an electron at n equals 1 with L equals 0, absorbing a photon jumping up to n equals 2, L equals 1, now has 3 options for the jump. It can jump to L equals 1, M equals 1, L1, M0, or L1, M minus 1. And these are all now have slightly different energies. So slightly different gaps, slightly different energies of photons, which can be absorbed in this transition. So now the photons coming in from the sun can be absorbed by more types of electrons or by more transitions of electrons. And that's what causes the split. So the Zeeman effect is something that it changes the opacity of the sun, of those regions of the sun, depending on the frequency and the magnetic field. Because obviously the darker lines are where opacity is stronger because there are more absorption processes. And opacity is smaller, or the sun is more transparent, where there are no such transitions. And so what you measure is the intensity of light coming out. It means that you can measure the strength and direction and polarity of the magnetic field. So we know sunspots are created by magnetic fields and have strong magnetic fields in them through the Zeeman process. Okay, we use it as an observational tool.
But we don't know what it comes from exactly. We just know that we just know from the Zeeman effect that it has some kind of a magnetic effect on the sunspots, but we don't know what kind of magnetic effects appear in them.
Right. So there's a lot of magnetic activity happening in the sun. We associate it with convection flows and with this differential rotation. So the sun is of course a plasma mostly. So there you have a lot of charged particles, electrons and ions. They're very hot, they move very fast, and they move around, and they can sustain magnetic fields. And we know that these magnetic fields are much stronger where there are these sunspots. We also know that these same magnetic activities, heightened magnetic activity, is related to other effects that disturb our sun or make it non-stationary. And that is the sun can spew out and throw away hot plasma and matter out of itself. This happens from day to day. This happens on a very normal and low intensity in what is called solar wind. Solar wind are just charged particles flowing out of the sun from the surface, mostly electrons and protons. You can trace the effect of this solar wind in multiple ways. The easiest one is if you look at a comet. A comet in the sky has multiple tails. And what distinguishes the different tails is basically the charge. Charged particles in the comet tail react with the ions and electrons coming out of the sun. And so they have a direction flowing outwards, as opposed to neutral material, which is not affected by the electrons and protons in solar wind. It's only affected by the radiation, so it heats and goes away. But it's a different direction than the ionic tail of a comet. So you can see that in comets. You can also see that if you put a sail or if you put a satellite, and that satellite can be bombarded by these charged particles in the solar wind. And our Earth itself has a magnetic field, which causes deflections of these ions and electrons as they interact with the Earth's magnetic field, as represented here in the middle plot on the bottom. And if you go far up north, you can actually see this. You can see this, and this is called the Aurora Borealis or the Aurora Australis, the northern and southern lights. So if you go to Norway or to the North Pole or to the South Pole, you can actually see these mists of color in the sky, in green and blue and all those northern lights. That's the effect of these charged particles coming from the sun and being deflected in the Earth's magnetic field. The Earth's magnetic poles are far north and far south, not exactly the north and south pole of the rotation. And the Earth's magnetic poles also change with time. But right now they're only a few degrees, maybe 5 to 10 degrees off of the poles. So you have to go pretty far north to see them. However, because this solar wind as well is associated with magnetic activity on the sun, it grows during solar maxima. So in years where there are more sunspots, there are also more solar winds. And that means that you can see the northern lights further south towards the equator, and the southern lights further up as well towards the equator. So if you're thinking of a good year to go to Norway, it's probably a solar maximum year. Solar maximum, you'll have more northern lights. More violent eruptions are solar flares. We can see that some of them can be quite large, much larger than the Earth. These are just eruptions of matter carried along the magnetic field of the sun. And coronal mass ejections, which are actual bulks of matter, hot plasma, carried by the magnetic field, but escaping the sun entirely. So they don't just erupt upwards and fall back necessarily entirely on the sun. Some of the mass can escape the sun and flow outward in the solar system. And if this reaches the Earth, it can cause a serious geomagnetic storm. So a magnetic storm on the Earth, on Gaia, caused by this material coming from the sun that's charged and hot. And it can disrupt satellite communication and cause damage to other electronic appliances because it's a large mass of ions and electrons flowing out of the sun. Also, more of this happens during years of of heightened solar activity. Okay, any questions so far about magnetic activity, solar activity, and all the ways in which our sun is not just a fixed, stationary, symmetric object?
Perfect. Do we know the cause of the solar wind, solar flares, or do we just assume it's from magnetic causes but don't know the specific cause?
So we know it's magnetic activity. We can see basically that these flows many times trace the magnetic field lines. So we know that it's magnetism that is doing it. We can associate the magnetism and the magnetic field to the solar dynamo, which is the sun rotating differentially and with convection sheets and convection currents and cells and all that. But understanding the mechanism is still different from being able to predict the mechanism. And so we can use this to learn more about the sun, but we're also, if we wanted to be able to predict this and use it for travel, for example, to know when it is safe and when you'll be hit by a solar flare, we're still not there entirely. We actually had a talk in our Astro seminar. I think it was 2 months ago in the beginning of March, 11th of March. A postdoc in Los Alamos National Lab, who actually works on, among other things, predicting solar weather or the weather coming from the sun using machine learning and other algorithms, which can be used to, among other things, to predict how dangerous it will be to travel, say, between the Earth and the Moon or the Earth and Mars, kind of give weather forecasts for solar activities and flares and mass ejections. But that's machine learning. That's trying to infer something from using artificial intelligence. Actual predictions of weather patterns and things like that still requires a lot more research into the sun's structure and activity.
Thank you.
Any more questions? Okay, let's take a break and continue at 1. Okay, so we talked about our sun, a completely normal main sequence star, and we saw that it has a lot of variability in some sense. On Earth, we see it because it's close. We see the magnetic fields changing through sunspots, other solar activity, flares, coronal mass ejections, stellar wind. We can have a fine-grained resolution of the solar surface and understand that it's changing. But what about other stars? Stars that have really dramatic global changes that we can trace. Those will be called the intrinsic variables. And we'll talk about many types of them, or at least mention many types of them, which we can also classify and locate them on an HR diagram. We'll start here on the left, which is the less busy plot. You can recognize, as usual, HR diagram. There's color or temperature on the bottom. There's magnitude on the left vertical axis. As you remember, magnitude goes negative as the luminosity increases, so negative is up. We see the typical colors. We can find our favorite main sequence here along the center with our sun around here, around the G2 main sequence star, and the giants, which we've discussed. But there are also these type of unstable or variable stars. And we see that they have kind of funky names, Cepheids, W Virginis variables, RR Lyra variables. And the naming convention, and we also see that they can kind of occupy different regions or shapes on the HR diagram. The names and the naming convention for variable stars is a bit tricky because we say that their luminosity is not constant, and as we'll see, their color is not constant. So how do we can't just classify them with position. So we name them after other stars that behave in a similar way. Basically, we have classes of variable stars. And each of these stars, in each of these classes and families, we take the first one which was identified in that class and name the entire class after that first prototype one. Okay, so how do we name a single star? We've mentioned this before. Typically, stars are named after the constellation in which they are located. Orion, Cygnus, whatever constellation. With a letter starting from A, B, C, and onwards, which indicates how bright they are. The bright, or alpha, beta, gamma, etc. The brightest star in a constellation will be, for example, Alpha Cygni or Alpha Orioni will be the brightest one. Beta after that, and so forth. But variable stars change their luminosity, so you can't quite position them in that ranking. And so they're instead of a letter indicating how bright they are, they're given a letter starting from R. R to Z, and after Z is over, you can have double R, etc. Similar to what Excel does when you run out of all 26 letters, it starts using double letters. And so you'll see that all of these variable stars can be RV Tauri, RR Lyra, T Tauri, and different types of variable stars will be named after the first one from the class, which itself will be named after the constellation and one of the letters from the end of the alphabet. And we'll talk about a few of these types of variable stars, mostly these Cepheid variables, and I think Lyra variables, and a few other types of typical variable stars. Long period variables in particular, here on the right. Okay, so let's see what they are. The first type of star, which again is almost variable or on the border of officially being considered a variable or a non-variable, is one of the brightest ones in the sky, Beetlejuice. Beetlejuice at times was the brightest star in the constellation of Orion, so it got the designation Alpha Orioni. It's a variable star, so it's not always the brightest one in that constellation. Sometimes it's actually the beta star, with Rigel being the brightest one. But when the catalog was formed, it was the brightest, so it got the designation Alpha. It's a red giant star. We already mentioned those. So it's on the HR diagram. It's in the red giant cluster of stars or area of stars. But it's a pulsating star. It beats and pulsates. It expands and shrinks, and its radius can actually change quite a lot. So we see that in an order of magnitude, the radius is about 1,000 times the radius of the sun, justifying the name red giant. It's a giant star. It's 1,000 times larger than our sun in diameter, in radius and diameter. That diameter itself is several astronomical units wide. So if Betelgeuse were positioned where our sun is, it would actually extend past the orbit of Mars and into the asteroid belt, almost all the way to Jupiter, just for a single star. Because it is so big and simultaneously so close, it's only 700 light years away, it's actually one of the largest stars in angular diameter as seen from the Earth, which means it's one of the very, very few stars, maybe only a few tens of stars, which you can actually have an image for covering more than a single pixel. So most stars just look like points in the sky, and even with the strongest telescope, they'll still only look like a point in the sky. Betelgeuse is one of those stars which today's technology, you can actually resolve with more than one pixel. It's that big and that close. And we can also see that it changes in size by about a factor of maybe 25 or 30%. It can get smaller and bigger, and following here, following Betelgeuse in the constellation of Orion for about 15 years, you can see that the magnitude changes by approximately a factor of 1. So of course, again, 1 here is dimmest and 0.2 or 0.3 is the brightest. And we recall that one magnitude is the square root of, is the fifth of the square root, or the square root of the fifth root of 100, or about 2.5. So there's about a factor of 2 in magnitude of Orion over this period, and we see that it's pulsates back and forth, and it's a semi-regular. It's not a perfectly regular sine wave or something like that. It's not a perfectly regular process, but it is semi-regular. So it changes more or less between the same extreme values and with a more or less given period. In particular, if we can look at one of the latest periods, and this happened just over a year ago, Orion became very, very bright and very, very dim on a very, very fast time scale. Here represented in about the course of half a year, from September 2019 to April 2020, so just a year ago. And we see that the magnitude dipped much more than its usual. It dipped by more than 1, so there's about 1.2 difference, so about a factor of 3 in luminosity and flux, went down and then went back up again. So this was considered a very interesting event to watch astronomically. You can actually see Orion becoming significantly dimmer in the sky. Okay, and at least for the regular pulsations, we can relate them to the radius growing or shrinking, thus affecting, of course, the surface area and affecting the luminosity by quite a lot. Any questions?
The variables considered to be stars that we can define in one category?
Variables are stars whose luminosity is not constant, or not even approximately constant. So we saw that for the sun, okay, there's a 0.1% change in solar activity. There's a gradual change over many, many hundreds of millions of years. Here we have a star that pulsates, changes its luminosity by about a factor of 2 every few years. So a factor of 2, you cannot consider that to be constant. We see that there's something going on. There's an effect here, and that's considered an intrinsic variable. Something in the star is causing it to appear different.
Okay, thank you.
Today, we actually think that this figure on the right, the last dimming of Orion, which was stronger than its usual, we're actually not sure if it was a completely intrinsic effect in the star itself, or if it was clouds of matter collected outside of the star, between us and the star, that caused this dimming. And that might be a cloud that originally came from the star, was expelled somehow, which caused higher opacity and less light to reach us. But at least on the left here, we have a definite periodic repetitive process. And this indicates some mechanism which has to be at work in the star to cause it to change so much. So by a factor of 2 and quite rapidly. Okay, but Beetlejuice is just a minor example. There's a factor of 2 here in luminosity. We have stars called Mira type stars, Mira or Omicron Ceti, so it's the Omicron star of the Cetus constellation. I think that's whale, that's Greek for whale, which are called long period variables. They change on a very long period, typically over 100 days for the period. And here we can really see a wave. We can see a period here that's very repetitive. And in magnitude, it's not just a factor of 2. This is a factor of about 6 or 7 in magnitude, which means it's about 1,000 or 10,000 times in luminosity. So many orders of magnitude. This is like 3 or 4 orders of magnitude, factors of 10 in luminosity. And this changes over a period of basically, in this case, less than a year. In less than a year, a star can be magnitude almost 2, so one of the brighter stars in the sky. And a few months later, it will disappear entirely. As you remember, the naked eye limit is about 5 or 6, so it can disappear beyond being able to see it with your naked eye. And if you were looking at this hundreds of years ago, as some people were, then it would be a star that appears and disappears from the sky throughout the year. And this was considered a great wonder when they first found it. And indeed, David Fabricius named the first star of this class that he discovered Mira, which comes from the same word as miracle, and other similar words in Latin languages. Mirabeau, words like that, the wonderful star. Mira is the wonderful. Discovered more than 400 years ago, again, with naked eye. And what he discovered was that this star drops in and out of sight. It dims and it brightens into sight and then dims out of the sky entirely. Today, we can locate this star around us. We know that it's about 300 light years away. We have a more or less exact measurement of the period, which is repetitive with a very, very steady period. We know that it's a red giant or in the red giant area, but unlike Beetlejuice, again, this is a much more stable and much more profound pulsating process or luminosity changing process. These pulsations of the radius can make this star very, very big or very, very small in orders of magnitude in the luminosity that we get. And we can calculate the relation between the luminosity of the star and the period of the star and other stars of the same class and get a very important tool in astronomy, which is a period luminosity relation. And the reason those are important is that if you know from the period of a star what its luminosity should be, then if you find a star with an observed flux, so an apparent magnitude, you can use a period luminosity relation to calculate its absolute magnitude and then to infer the distance. So these kind of variable stars provide us a way of measuring how far things are in the universe, which we could not otherwise do. And we'll talk about that a bit more when we talk about Henrietta Swan-Leavitt and Cepheid variables. But here's a first example of a really cool variable star. It changes by about 1,000 or 10,000 in luminosity and brightness over a period of less than a year. So long period variables. Here's another example, Chi Cygni. So this is a star in the constellation Cygnus, which I think is a swan in Hebrew, in Greek. And we see again that we have a period that's quite repetitive, quite accurate, and changes even 10 magnitudes. So more than 100,000 times difference in brightness between the peak luminosity and the minimal luminosity. And we can also do spectroscopy and analyze how the star is behaving. And we can see the pulsations in the apparent magnitude and plot them together with the variation of the periods in temperature and radius and in luminosity. And we can find how these different, of course, when the star gets bigger, the temperature escapes from further out. So the temperature basically goes down when the radius goes up, but it's still a large enough effect, a large enough pulsation to create a very, very large difference in magnitude, so in luminosity. And again, this factor of about 100,000, about 10 magnitudes, happens over about half a year. 204 days is the period. So this happens very, very fast. These pulsating stars can be quite impressive. Cepheid variables, named after the first star of the class, Delta Cepheid or Cepheid, depending on your transliteration of Latin Cs. The first one was discovered in the constellation of Cepheus or Cepheus, which is in the northern part of the sky. You can identify here it next to Cassiopeia. In the Greek mythology, this was Cassiopeia's father. So he's between Cassiopeia and the North Pole, the polar star Polaris. So these are quite northern, a northern constellation. And it was very interesting. It was discovered already in the 18th century by an amateur astronomer called John Goodricke. We'll talk a lot about Goodricke in today's class because he discovered many types of variables and also explained many types of variables. And it's worth mentioning maybe that he was deaf from a childhood disease. And so he couldn't get a decent job. So he worked as an astronomer where he only needed to observe and not to speak. And he was very sick. He died at the age of 21. So all of his discoveries were made about the age of 20 and 21, including this one, the first Cepheid variable star, Delta Cepheid, about 900 light years away, which is not a long period variable, it's a short period variable. It has a period of about 5.5 days. So John Goodricke was looking for variable stars. He was working at the observatory with his neighbor, Edward Pigott, who found another variable star called Eta Aquila in the constellation of Aquila about a month earlier. And that one has a period of 7.2 days. So they started noticing more and more stars which varied a lot in their magnitude over a very short time. And again, you can see here on the left bottom, Delta Cepheid's magnitude curve as a function of time. And you can see that over a period of, here we have 2 cycles, so about 10 or 11 days, it changes by about a factor of 1 magnitude. So routinely by about a factor of 2 or 3 in luminosity. On the right, we have 2 stars. We have W Sagittari in the constellation of Sagittarius, Kashat in Hebrew, the archer, and in the right, Eta Aquila. And we see over very few days, again, in order of 10 or 20 days, we see that the luminosity magnitude can grow by a lot. Here from about 3 to 4.5. On the right, we have from about magnitude, I think it's again order of a few. Pulsations don't need to exactly repeat themselves, but we see that the shape of the luminosity curve is in general repetitive. So these stars, if you consider their distance and magnitude, are a lot brighter than our sun, 1,000 to 100,000 times, or 500 to 300,000 times brighter than our sun. And they have short periods relative, about 1 to 100 days in a period of this luminosity changing from minimum to maximum. Okay, so these are Delta Cepheid variables. They're short period variable stars. I mentioned before that these are very useful, and the person who discovered that they are so useful was here on the right, Henrietta Swan-Leavitt. She found, and her original plot from the original paper is here on the left. This is not a reproduction, it's an actual picture from the original paper. And it shows that the magnitude, which as usual is on the vertical axis, changes with the period. So she found many different Cepheid variables, and for each of them plotted the peak luminosity as a function of the period. In this case, I think the top curve is the peak luminosity, and the bottom is either the minimal luminosity or the average luminosity. And it seems that if you follow, that you can pass almost a straight line between these different observations. So different stars, different luminosity. Each star has different luminosity and different period, but they all seem to obey this kind of linear relation. And so she drafted this relation. She approximated the numbers on this curve, and she found that the magnitude in visual light of these stars is basically given by this linear coefficient. Of course, it's minus because the curve goes up, and we remember that magnitude decreases as luminosity grows because it's an inverse scale. So there's this linear coefficient times the logarithm of the period, which means if we basically luminosity converted to a log scale will give us magnitude, and period converted to a log scale will give us this log of p. And we have a linear relation. And this is a fit to this curve on the left. And this fit is immensely important because this gives us our first notion of what in astronomy we call a standard candle. So a standard candle or a standard measurement of what something should look like tells us that if we know how much light an object should emit based on any consideration, and we measure it somewhere in the sky, then by comparing how much light it should emit and how much light we receive from it, we know the exact distance, right? You've all had this experience in the homeworks trying to measure parallax or measure distances to objects in various methods. And it's hard because we have no depth perception in space. But if we know how bright something should be at some standard distance from it, some absolute distance from it, and if we know how bright we see it, that is, if we can compare the absolute magnitude to the apparent magnitude, then the ratio between them, or the difference between them, will basically give us the distance, or the ratio of the distance to the standard distance 10 parsecs. So here, this calculation of absolute magnitude in the visual band can be used to tell us how far something is. And now if you can calibrate your ruler, which measures distances, if you can calibrate this relation with nearby Cepheid variables in our own neighborhood, that is variables which we can calculate parallax for, so we know the distance and we can calibrate the true luminosity, the absolute luminosity to the period, then if now we find a Cepheid variable which is very far away, even outside of our galaxy, all we need to do is measure its period, find the period on this plot on the left, find the absolute luminosity or the absolute magnitude and the luminosity, measure how bright we see it, and we know the distance. And this is in fact how what was later used to calculate the distance to Andromeda, the nearest galaxy, and to actually prove that it's a separate galaxy by comparing the brightness of different Cepheid variables using this fitting function of the Henrietta Swan-Leavitt. Okay, so standard candles are used in this way. If you know the source and you have a measurement, you can infer the distance. Any questions? Okay, I'll say that today we have more types of Cepheid variables. We don't just have one class. And in fact, even back then, there were more than one. They saw more than one type, but they didn't know that it was more than one type at the time, which caused some errors in calculating the galactic distances. But now we distinguish between classical Cepheid variables, which is the blue curve here on the bottom, and type 2 Cepheid variables. And when you analyze a variable, a Cepheid for distance, it's now understood to be important to know which of these plots you're on, because they have slightly different period luminosity relations or period magnitude relations. And so we'll skew or give you wrong measurements of the distance. So this was entirely empirical. Of course, we remember Henrietta Swan-Leavitt from the Harvard computing group the women who are working at the Harvard College Observatory, analyzing spectra of stars and classifying different types of stars. It gave no physics for why this happens. It only gave a fit for using these for measurements. And the first person to explain the actual measurement was Arthur Stanley Eddington a few years later. And he proposed what's called the kappa mechanism, which was later worked out a long time later by Sergei Zhivakin. And they together give this notion of what's called a helium valve. Valve means like a faucet, like which you turn to get more water or less water. So you regulate the amount of light or luminosity coming out using this valve or this kappa mechanism. Kappa, as you might recall, is the letter we use to mark opacity. And this is, as they inferred, an opacity-driven process. And all you need for this to work is to have a form of opacity kappa, which grows or becomes more opaque with temperature. So the hotter it gets, the more opaque, the higher the opacity. Today we know that this can be a source for this type of opacity can be, for example, helium, but you can think of others, and it doesn't change the basic mechanism, which works like this. Imagine you have a star, and the star shrinks. Okay, as the star shrinks, it becomes denser, and so it heats up. If it heats up, as we said, kappa increases, you get higher opacity. If you get higher opacity, that means that the radiation pressure coming from below increases because more of the photons trying to escape can't escape. They're absorbed or scattered or hit the helium or other material particles in the star. So the pressure that the star has to sustain increases. That means that the star expands back. So if it shrunk, it heated up, opacity grew, pressure grew, it expands back. And the other side, of course, as it expands, it becomes less dense, it cools off. If it cools off, then opacity decreases. That means that the energy created inside can now escape. It goes outside. It doesn't pressure the star as much anymore because it can just escape. So the star undergoes less pressure and shrinks back in with gravity. So if we recall that 2 weeks ago, we discussed hydrostatic equilibrium. Obviously, these pulsating stars break hydrostatic equilibrium, but they're not far from it. We still have gravity balancing out pressure, but now we have these modes of growing radius and then decreasing, growing and decreasing, and we're kind of periodically perturbing or floating around in a repetitive manner around hydrostatic equilibrium. And this kappa mechanism provides us a driving mechanism or a driving force for these pulsations. So that's the Eddington mechanism, the kappa mechanism. One possible way of explaining these pulsations of a variable star, intrinsic variable star. Any questions? Okay. So we mentioned the distance ladder and how these cepheids can be used to measure distances. And so this is maybe a good time to present the astronomical distance ladder for observations. And it's called a ladder because it's made of rungs, shlavim in Hebrew, one after the other, one step after the next. And we covered the bottom of this already. We started this course actually by calculating the radius of the Earth, as the Greeks had done 2,000 years ago, using the distance of the Earth to calculate an astronomical unit, distances in our own solar system, distance to the moon, to the sun, and other distances, with Earth-based parallax to different planets. We can then use the diameter of the Earth's orbit around the sun for parallax of stars outside the solar system, when now the baseline for the parallax is 1 astronomical unit, whose length we know from solar system-based parallax, which we can do based on the radius of the Earth. This stellar parallax we mentioned can give us an idea of the distance to stars, which are approximately 1 arc second away, or maybe a few parts of an arc second away. So distances up to maybe a few hundred parsecs. That's not even enough to cover our own galaxy, which is about 8 parsecs away from us, or 7.6 kiloparsecs away from us. But these variable stars, here we have 2 of them, RR-Lyra variables and Cepheid variables, can give us much further distances. They're much more bright than the sun. Recall that they can be 300,000 times brighter than the sun, which means we can see them approximately 300,000 times away, further off. If we can measure their period, then we can calculate what their luminosity should be at the source, compare it to the luminosity that we measure, and know the distance. And all we need to calibrate this is some RR-Lyra stars, which are close enough to us to calculate regular stellar parallax for calibration of the scale. And then we can use them even beyond where we could do stellar parallax. And so we can use these RR-Lyra variables to calibrate the ladder up to the next rung, which is Cepheid variables. And so we can find distances to Cepheid variables in our own galaxy and calibrate them as far as Andromeda and farther away. So now we're talking megaparsec distances. And we'll talk about the next 2 rungs, type 1a supernovae and cosmological distances, Hubble's law, later in the semester. All of these will be calibrated based on earlier rungs of the ladder or lower rungs of the ladder, going all the way down to calculations that we can do with measurements on the Earth itself, extending the reach of our distance measurements as we go up in the ladder. Any questions?
I have a question about something earlier.
Mm-hmm.
The absolute magnitude.
Yes.
Henrietta is her name, found.
Yes.
How did she do it again with the period luminosity relation?
Look at the plot here on the left.
Mm-hmm.
It gives log of the period on the horizontal axis, and it gives the log of the luminosity, which is basically magnitude, on the left side, in its absolute magnitude. Okay, how do you calculate the period of a star? That's easy. You follow it for a year. It has a period of, you see, between about a few days to maybe 100 days. These variables, log p minus 10 of p minus 1 means that if it's 0, it's 10 days. I'm sorry, if it's 0, it's 1 day, and if it's 2, then it's about 100 days or something like that. So you follow it for a year, you get a few periods, and you can find the x coordinate, the horizontal coordinate. How do you calculate the absolute magnitude? Okay, so again, you follow it. You find the maximal apparent magnitude, that is how luminous you see it. To convert that to absolute magnitude, you need to know the distance. So that's the tricky part. You cannot do it for any star. You'll have to do it for a star that's close enough for you to calculate the distance in any other way. For example, parallax. So if you have a variable that's close enough that you can calculate its apparent magnitude and its period and its parallax, then you know the distance. And so distance squared times flux gives you the luminosity, right? So you know the absolute magnitude by converting the apparent magnitude using the distance. I think we did this in like week 2 or something of the semester.
Mm-hmm.
So that gives you the vertical axis, absolute magnitude. And you do this for a bunch of stars. Maybe there are like, I don't know, 20 stars on this plot. And then you find the line that best fits approximately. It's not exact, but find the line whose slope best fits all of the points, or fits most of the points as best as you can. And the slope of the line will give you dm to d log p. Or basically, you fit a line. Today you can do this with a regression, or you can ask Excel to give you a linear estimate of a line between points. And you can also calculate it, and this is basically what you get, or what she got.
Okay, so she just fit a line to a bunch of stars we know that behave similarly, and then we can from that deduce the absolute magnitude of further away stars.
Exactly. She plotted the empirically observed periods and luminosities for a bunch of stars, assumed they were all of the same class, so behave the same way, and then fit a line to project how other stars should behave if they belong to the same class.
Okay, I see. Thank you.
Okay. And that's how you build a distance ladder, one rung after the next. And variable stars are a crucial step in this ladder, a crucial rung in this ladder. Okay, so here again is our classes of variable stars. We mentioned these delta Cepheids. We saw these Lyra variables. On the distance ladder, we mentioned the long period variables, Mirai type variables. As you see, there are many other types of variable stars, which we won't go into this course, but it's good to know that stars can intrinsically display all these different types of behaviors with period and luminosity changing, and how important these are for later mappings of the galaxy and outside the galaxy. And indeed, the cosmology of the universe began with these, the modern cosmology began with these measurements of distances coming from variable stars. And again, the reason it's so important is because for a regular non-variable star, you only have two parameters. You have the luminosity and you have the temperature. But you don't know much more than that. For these variable stars, you have an added parameter. You have the period as well. And with one more parameter, you can project many more relations and calculate the distance with better accuracy and to further away. Especially since these stars, you can see, are generally above the main sequence. They're much brighter than our sun. Okay, this is probably a good time for a break. Let's reconvene at 5 minutes to 3. Okay, so we talked about stars which don't vary a great deal. We talked about intrinsic variables which do vary a great deal because of internal pulsations and mechanisms in the star, which cause their luminosity to change a very great deal, orders of magnitude, and many orders of magnitude in luminosity. And the last topic for today is extrinsic variables. That is stars whose luminosity changes. We'll see that it also changes periodically, but it doesn't change because of something happening inside the star. It changes because of something happening outside the star, some extrinsic effect. And that effect is, in general, coming from the presence of another star or another object, not even necessarily a star, but something else, another star, planet, black hole, another partner is in the system, and they're affecting each other. And this mechanism was actually suggested by the same John Goodrich we mentioned before. And to explain these type of periodic changes. And the most interesting or the most famous classical example of these types of double stars, or more specifically, eclipsing double stars, that is where one star comes in front of and eclipses the other, something we all know from our own solar system with solar and lunar eclipses, and transits of Mercury and transits of Venus. The most famous example of this is the star Algol, the beta star of the Perseus constellation, here depicted in a classical artist's rendition. So the stars are in their places, and you can find all of your favorite constellations around here, Cassiopeia, Andromeda, and Perseus. Of course, the completion of the art form is not there in the sky, but it's interesting to note that Algol was not just given to, the name Algol was not given to just any one of these stars. It was given to the head of the monster. It was considered a demonic star. Algol comes from Ras Al Ghul, or the head of the monster, Rosh Satan in Hebrew, and in other old languages, the Gorgon's head in Greek. Because the stars were considered to be heavenly and stationary, at all times a star which was obviously variable, you can see it with your own eyes, that it flickers and dims, becomes dimmer, was considered satanic and evil and monstrous, and it was given therefore the name of the monster's head. And this was known for over 3,000 years as a star which dims. It's not fixed in the sky, and they kept close watch on it. And today we know that the star is actually quite close to us, only 90 light years away, and typically quite bright, magnitude 2.1. Not surprising, it's only the beta star, so the second brightest in the constellation of Perseus, a familiar one. But it has periodic drops in magnitude by more than 1 magnitude. So by about a factor of 3. In luminosity, dropping from 2.1 to 3.4. And John Goodrick noticed that this is a very, very periodic dimming. It lasts for about 10 hours every time, and it repeats every 2.87 days. So in every less than 3 days, it dims for about 10 hours. And he explained that this period can be explained by a double system, a double star, where one passes in front of the other and reduces the amount of luminosity that reaches our own eyes. Today we can make out individually these two stars, Algol A and Algol B. Typically the brighter one is called A and the next bright B in every star system. And so we have an actual image here on the right from a telescope of these different stars. We see Algol A and Algol B. They're very, very close to each other. They're about 6% of an astronomical unit apart, so much closer, about 7 times closer to each other than Mercury is to our sun. And unlike Mercury and the sun, which are a 1 solar mass star and a very small planet, which is less than 1/1,000,000th the mass of the sun, Algol B is only between 3 to 4 times, or sorry, 4 to 5 times lighter than the main star, than Algol A. So they're a 3.2 solar mass star and a 0.7 solar mass star. And of course, you can, if you know the masses and if you know the separation, you can calculate the period, or what is actually more easy to do in an astrophysical calculation, the period you can measure quite well and could do it 250 years ago. And then if you know the distance, for example, if you can make them out with a telescope, then you can find the masses. Or alternatively, you can use the spectrum of each of these stars to calculate the luminosity and the temperature and the position on the main sequence of the HR diagram, infer the mass, and then use the masses and the period with Kepler's third law to calculate the distance. And today we can actually make these out with a telescope. Today we also know that this binary system is actually a trinary system. There is a third companion almost 3 astronomical units away, so about the distance of the asteroid belt from the sun. And Kepler's law will tell us that if something is much farther away, then it has a much longer period. It rotates much more slowly. In this case, a period of about 2 years. So it's actually a trinary system, but recognized at least as a binary already in the late 1700s by the same John Goodricke, who won an award for the discovery, but died before he could receive it. So looking more accurately at an eclipsing binary system, we typically distinguish between the primary and the secondary. The primary being the one providing most of the light and the secondary providing less of it, typically the smaller one. And we notice that in a period of orbit, there are actually 3 things that happen. Most of the time, the 2 objects are not blocking each other. They're one to the side of the other. And so we have the maximal luminosity. We see all the light from both stars together. We can't always tell them apart. Typically, we'll only see 1 pixel in the sky from both of them. And so all we'll have is the brightness, and we'll have a steady bright line. However, when the secondary blocks part of the primary, we'll have a strong dip because the secondary is smaller and typically colder. Then per unit area, it has a lower temperature and a lower flux. So a lower luminosity. And if you recall, luminosity per unit area goes like temperature to the 4th power. That's Stefan Boltzmann's law. So even if a star is only slightly smaller and slightly colder, it will be a large decrease in luminosity. So this red star will block a lot of the yellow light. Yellow is hotter than red. And so we'll have a strong dip. Typically, this dip can actually be longer on the bottom, because if the star is really a lot smaller, there will be the transition time as it goes from one edge of the primary to the other from our point of view. And it will also have these fall and rise features. So we'll have a bright star, then it will decrease, stay at the lower level for a while, and then increase back up. So the timing here will give for Algol A, this is a 10-hour drop, repeating every 2.87 days. There's also a secondary eclipse, a secondary drop, which happens when the secondary is behind the primary, in which case the secondary doesn't block the light from the primary, but the primary blocks the light from the secondary. And so even though the primary is brighter, we'll still get less light because we're only getting the light of the primary and not the light of both of them, which was the long high plateau. So you recognize an eclipsing binary system by these 3 features. It's typically stably high, you have a large dip, and you have a small dip. And the durations of both dips will typically be similar, at least if it's a circular system. If it's an elliptical system, then there can be a difference because the angular velocity of the secondary will not be constant. But if it's a more or less circular system, then these durations should be similar in time and duration, but not similar in depth, in difference of brightness. Okay, so those are types of eclipsing binaries, which are physical. They are an actual bound system. The 2 stars orbit around each other. They're physically close to each other, and they are actually one system. Typically, with our naked eye, and even with some telescopes, it's impossible to tell a real binary system apart in the sky. And most of what people in popular parlance call a double star or twin stars are actually only what's called optical doubles or apparent doubles or naked eye doubles. The most famous example of these are in the constellation of Gemini, or Mazal Te'omim in Hebrew, and they are the twin stars Castor and Pollux, considered the heavenly twins since the times of Greek mythology. They look like they're close to each other in the sky, but they're actually very far apart from each other. They're about 50%, their distance from each other is about 50% for their distance from us. So they're quite far away, 34 light years and 51 light years from us. And the only reason that they look close to each other in the sky is because, again, we don't have any depth perception when we look into space. So we can think of us being here on the Earth, looking at stars A and B, which we can see here are very far from each other if you consider the view from the top in this example. But from the Earth, in angular separation, they look much closer to each other. So they look like twin stars. It's an apparent twin, but they're not actually a bound system. They're basically unrelated to each other. They're just random stars in the sky. One of them can be much, much, much deeper or farther away from the other than the other from us, but they look to be close to each other. So those are not real binary systems. They're optical binaries or optical doubles. The parameter that distinguishes a real physical system from an optical binary system is that it has to be gravitationally bound. So they have to be close enough to each other to actually be in each other's potential well with a net energy that's negative. That is a kinetic energy, which is, of course, always positive, but a potential well, which is deeper than the kinetic energy. The Virial theorem will give us a factor of 2. And so the total energy, EK plus EP, will be negative, meaning it's a bound system. In that case, the stars can be considered orbiting each other or orbiting their mutual center of mass. And we cannot typically see them with our own eyes. We have to look at some parameter of the system during eclipses, if we're lucky, or during other types of interactions and effects on each other, and effect on the light coming to us, in order to tell that they are, in fact, a double system. They look like one point in the sky when we look, because they're too close to separate, but we can use other measurements to tell them apart. An interesting point is that there is one pair of stars in the sky, which you can see with your naked eye, if you have good eyesight and go far away from any place that has industrial city lights. Actually, it was considered a test of eyesight to soldiers in the Roman army. It's a pair called Mizar and Alcor, the horse and the rider. It's a pair of stars very close to each other in the constellation of the Big Dipper, also Major. So you can see them then basically from anywhere in the Northern Hemisphere. And here we have them in an actual image of the sky. This is the Big Dipper. You can probably tell it apart if you've ever looked for the Northern Star. And in the handle of the cartwheel, you can find these both stars, and here they're amplified apart, or there's a magnification here to show them apart. If you have really good eyesight, you can see this with your own eyes. And why these two stars are interesting is that we actually do not know whether they are a bound system or not. We know approximately how far they are from us, 0.36 plus minus 0.19 light years from each other. We know how far apart they look in angular distance from our vantage point, which is 12 arc minutes. So they're closer to each other than a full moon, about a half or a third of the diameter of the full moon. So you can tell them apart, but sometimes it's not easy. Not everyone can do it. But we don't actually have a good measurement or a good enough measurement to tell whether the kinetic energy is above the potential well or below. So they could be just random stars close to each other. They could actually be a bound system, but we don't know yet. So that's the only case where you might actually be able to see a bound system in the sky, but we don't know. And we'll talk more about both of these when we talk about how we can actually measure physical systems, physical binaries, and tell their different types apart. But basically, other than those two, for which we don't know, every other pair of stars you see in the sky are close to each other, are only an optical or apparent binary, and not a real bound system. So the next type of binaries are visual binaries, not optical or apparent, but visual binaries. And those are stars who are physical systems, they're a bound system. The definition of what constitutes a visual binary actually depends on whatever technology we have available at the time. For example, here on the right, we have the Sirius system, which you already saw, I think, in a tutorial. Sirius A, one of the brightest stars in the sky, was recognized in 1844 to wobble a bit in the sky. And if you can tell the presence of a companion star by the motion of the first one, so you only see one of them, but you see it behave in a way that indicates, whose motion indicates the presence of another, that's called an astrometric binary, because you can do astrometry, you can measure one star to infer the presence of the other. So Friedrich Bessel, whom you know from math, found Sirius to be an astrometric binary. And about 20 years later, a telescope finally found the companion, here the small one, a white dwarf called Sirius B, and made these pair from an astrometric binary into a visual binary, where we can actually see both companions, both primary and secondary. Mizar itself, from the Mizar and Alcor pair, was recognized itself as a binary system, a visual binary. And this happened already with almost immediately with the invention of the telescope in 1617 by Galileo Galilei and his student Benedetto Castelli. And it was already the most simplest telescope of the time was able to tell them apart. They're about 14.4 arc seconds apart. So about 60 times closer to each other than Mizar and Alcor are to each other. They were 12 arc minutes and these are 14 arc seconds. And that means that it's an elliptical orbit, but they come close to each other, as close as 380 astronomical units. So if you calculate the masses and you know the distance, you can infer the period. In this case, it's a very long one, thousands of years of a period. So we have not yet seen them complete a revolution, but we can follow them in the sky and see that they're very, very close together, yet somewhat apart. And we've been watching them for more than 400 years now. A visual binary. You can actually tell those two stars apart. Visual binaries are great. They're great for amateur astronomers. They're great for tracing with testing your telescopes or actually studying both stars separately, which is something we can't do for other types of non-visual binaries. Here we have 3 more examples. Kruger 60 on the left. You can see the primary on the upper right, and you can see the secondary circling around the primary. In this case, we can see that about 1/4 of a period takes about 12 years. So there's about a 50-year period here for Kruger 60. And you can follow that visual binary system in the sky. Gliese 623, this is a Hubble Space Telescope image. You can see the primary and the secondary only about 2 astronomical units away. So much closer and with a faster period. Here on the right, you can see another nice star, the 70th in brightness in Ophiuchi, or 70 Ophiuchi system. And you can see that it's been followed in the sky, the secondary, around the primary, for a full orbit of about 90 years. Already from 1825, followed all the way through year by year through the 1890s and until the 1910s. Of course, the fastest part of the orbit you can see here was around the turn of the century, around 1890 to 1900, when the stars were closest to each other. This is, of course, Kepler's second law again, and slowest when they're far away. And if you add another 90 years to this, you can find that the last closest approach was about the 1980s, so around the time I was born, and now it's already kind of in the more distant part of the period again. So these are visual binaries. Any questions about visual binaries? Okay, an interesting point that's worth mentioning is that we can see from these at least two examples here, Kruger 60 and 70 Ophiuchi, that the plane of the orbit is not directed towards the Earth. That is, we see it most clearly on the left. The star is orbiting around, the secondary is orbiting around the primary, but it doesn't block it. That happens on the right side as well. This is not an eclipsing binary system. It's a visual binary, but we can see both of them. But if you look at it only in terms of brightness, the brightness is always the same because it never happens that one of them blocks the other. And if you consider it, it's actually quite rare for a binary system to be an eclipsing binary because of all the orientations of a plane in the sky, it takes quite of a coincidence to be aimed directly towards us along our line of sight. So visual binaries are, non-eclipsing binaries will be much more common if you randomly position stars in the universe or in the galaxy in this case. That doesn't mean that they're easier to find, but it means that they're at least more common. Spectroscopic binaries are a pair of stars where you typically cannot tell them apart with a telescope. So they're not a visual pair. You can't distinguish between them by seeing 2 points of light separated from each other. But what you can do is you can do spectroscopy of the system and find that not the brightness changes. The brightness does not change with time. The positions do not change with time. You cannot make the positions individually, but the spectral lines change with time, change periodically. And this again happens if the velocity of rotation of the system has some component aimed towards us. If we're completely face on, if they rotate in a plane perpendicular to our line of sight, then it's hopeless. We'll have no effect of line of sight velocity. But if there's some inclination angle of the plane of the orbit towards us, then there will be some angle I between the line of sight and the plane, and the sign of I will give us the component of the velocity aimed towards us. And what we remember maybe from the third week or from relativity or from other sources is that we have Doppler shifts. When a source is in motion relative to us, there is a Doppler shift in the frequencies or in the wavelengths or in the colors of light coming from that source. What that means is if you know something about the spectrum of the star, for example, if you can measure spectral lines, you can compare it to where you expect those spectral lines to be in a stationary non-moving source. And as the star moves, if it moves towards us, those lines will be Doppler shifted towards the blue, the higher frequencies. And when it's moving away from us, the same lines will be Doppler shifted towards the red, to the lower frequencies. What that means is you can follow through a period of the star by following periodic motion of the Doppler of the spectral lines. They'll move towards the blue when it's moving towards us and towards the red when it's moving away from us. And because it's a binary system, sometimes you might even be able to see the spectra of both constituents simultaneously. And you'll see lines of one moving to the blue and to the red, simultaneously with the lines of the other moving to the red and to the blue. So they'll kind of, I'm obviously exaggerating the effect a lot. This will require an ultra-relativistic shift, but something like this is something that you can find, this periodic motion of the spectral lines of the spectrum, red and to the red and to the blue between both of these stars. If the stars have different masses, then these velocities will be different by the ratio of masses. Of course, the massive star will move slower, the lighter star will move faster, so you'll get an effect that looks like this. Okay, this pulsation, this repetitive motion of the massive star moving a little and the lighter star moving a lot faster in the opposite direction. And then you can trace the velocities of both of these companions and infer from this periodic motion that it is in fact a binary system and not a single star. We mentioned MISA, which was a visual binary system. You can tell both objects apart, MISA A and MISA B. As we said, they are 14.4 arc seconds apart. But spectroscopy can tell you what you cannot do with a telescope, which is that MISA A and MISA B are each of them in themselves a binary system, a spectroscopic binary system. So MISA A was identified with spectroscopy, so not surprisingly by the same Harvard spectroscopy group, Antonia Maury, working at the Harvard Observatory with Pickering. She was, as we mentioned, one of the first women to work in the observatory. And they identified the period of about 20 days, 12 hours, 20 and a half days. And they used this spectroscopy not only to measure the composition of each of the stars, but to measure that the star is in fact a double star, a spectroscopic binary star. About 20 years later, Frost and Ludendorff recognized MISA B was also a spectroscopic binary. As you can see, the period here is about 10 times longer, which means the velocities, which of course means the separation is wider, which means the velocities are weaker, which means this spectroscopic identification is a lot more difficult. But even that you can still make out and could make out over 100 years ago and realize that MISA B itself was also a pair, a spectroscopic pair. Any question about spectroscopic binaries? Okay. The next pair, eclipsing binaries, we already mentioned. This is in kind of the opposite case to visual binaries. In this case, it doesn't help you that if the plane is perpendicular to you, which makes them farthest away and easiest to tell apart with a telescope, it also makes them insignificant for eclipsing searches. For eclipses, you need the plane of the orbit to be directed directly towards you along the line of sight. And then you have this periodic dimming in luminosity. As we mentioned, the large dip when the primary is behind, and the secondary dip when the secondary is behind. And they block each other, and you can measure, as we mentioned, the time that it's flat on the bottom. That's the time of transition. You can measure the time of the gradient, the time of the change, the fall and the rise in both cases. And that's the time that it takes, that basically gives you the size of the smaller object for how long it takes to cross into the larger one. The large bottom dip tells you how big the large one is from how long it takes the small to cross, to move across it. And the time in between, the period, will tell you in some sense how far away these objects are using Kepler's law. This again is a very rare condition if you consider that they have to be aimed directly towards us. But because if it happens, you have many more data points that you can measure, much more data you can extract from these, and it's a very typical signal to look for. We actually have know a lot of these, and they're actually maybe the easiest ones to find if we cannot tell the two bodies apart. And a classical example of these, of course, are planetary systems. Because if you have a star and a planet, the planet typically has completely insignificant luminosity. It only reflects part of the sunlight or starlight that hits it. So making it out visually as a visual binary is next to hopeless. But if the planet is big, say Jupiter size or something like that, today we can do even better. If the planet is big, then when it blocks some of the star, you can actually tell that it's there. And that's how planets have and are being discovered. And now we know thousands of planets around stars around us, mostly found with these methods of finding eclipsing binaries. Any questions?
I was wondering, most of the binary systems that we see here is like a smaller star rotates a bigger one, the main one.
Mm-hmm.
I was wondering if a system of two almost equal mass stars orbiting each other exists, and if it's stable, because it doesn't sound like a stable system to exist for very long, I don't know, in my opinion.
Why would it not be stable?
It just seems like it would like collapse into each other. If it,
why? What would drive the collapse?
it seems like a very hard, how do I say it? Like very difficult conditions for them to strike each other at the same angular momentum at the same time to be stuck in a stable motion. I think, I don't know, I'm not sure.
Okay, so there's a question, there are a few questions here. Let's start with maybe the first one. Stability. If you have a system, a binary system, typically it will be stable. We know that the two-body system is stable in Newtonian mechanics, and if they're not too close together, then Newtonian mechanics is basically all you need. There's no reason for them to be disturbed, perturbed, or to lose stability. It is true that to say two equal-sized systems, so objects, you need to ask, how do you define equal? Because of course, it's the exact same number of atoms, you'll never find two stars with the exact same number of atoms. But if you're willing to accept 1% off, 10% off, or something like that, then one can argue that you'd actually expect most star systems to be quite similar in size, because if they're produced from the same mechanism, then there's no reason to break symmetry for them to be a lot different from each other. Of course, we saw here factors of 3, factors of 4. These are not considered big numbers in astrophysics. Also recall that the main sequence only extends from about 1/10 of a solar mass to about, say 100 solar masses. So there's about a factor of 1,000 there, which is not a lot of playroom, right? And you expect stars to be of approximately the same age if they were produced together. The massive stars run out quickly. So if you see an actual bright system, they might be of actual very similar masses. Of course, there's the case of planetary systems where you have one star, which is big, and one or more planets, which are 100 or 1,000 times smaller. And that's what we have in our solar system. Jupiter is about 1,000 times lighter than the sun, and the rest of the planets are even smaller than that. So you can find all of these different options in the sky. As for forming them, you named one formation mechanism, which was random stars catching each other and becoming a bound system. That might not actually be the most common way to form a binary system. It might be a lot easier to form a binary system if you just have a cloud of protostellar material exceeding the Jeans mass and collapsing simultaneously at multiple nucleation points. And as we discussed, I think it was last week, maybe 2 weeks ago, conservation of angular momentum would favor producing a multiple star system rather than just a single one. It's actually more easier to produce a stable system if you have a partner to give off your angular momentum to.
Okay, that makes sense. Okay.
Other types of physical binaries, we mentioned the second group here, astrometric binaries, which are cases where you don't see the partner, but you can infer that it's there only based on the motion of the first. This can happen, for example, this is basically all you can do if they don't pass in front of each other, so there are no eclipses, and if the partner is dark, so very, very small, like a neutron star or a black hole, or even a planet. If it's dark, and so you don't see it on its own, it won't be a visual binary. If it's not on the plane, it won't be an eclipsing binary. The thing you'll have left is basically this astrometric measurement. And we actually have many types of these stars identified. Here on the bottom right is an excerpt of a few orbits of bodies around the center of our own Milky Way galaxy, around this black dot in the middle, which we have never seen in actual light from. We can't see it with a telescope. It's small and dark. We think it's a black hole, the Sagittarius A star, the black hole at the center of our own galaxy. And we think it's a black hole because two groups of scientists led by Reinhard Genzel and Andrea Ghez, who won the Nobel Prize for this discovery earlier this year. Their groups traced these other stars in the center of the galaxy and found that they all have elliptical, more or less circular or elliptical orbits with the same focus. So all of them orbiting basically the same point at the center. Calculating the periods and the radii or semi-major axes of these ellipses, you can use Kepler's law to infer how much mass would be required at the center of this system to hold all of these orbits together moving so fast. All of these orbits, they close in a matter of a few tens of years, not much more than that. And these distances are huge. And they calculated the mass required at the center is about 4 million times the mass of a sun. So 4 million times the solar mass, yet emitting no light. The strongest candidate we have for such an object is a supermassive black hole. And that's how it was first argued convincingly that there is a supermassive black hole at the center of our galaxy using astrometric data, or basically claiming that it's the center of an astrometric multiple star system. Photometric binaries are somewhat easier. You can find the effect of the secondary on the primary by actually changing its luminosity. And this can happen in many minor physical processes. Light from one can reflect off of the other. They can pull each other's shape and change it because of tidal effects. This is another mechanism that our favorite John Goodrich proposed in Betelgeuse stars and other types of variable stars. One of them, it's an extrinsic mechanism. One of them changes the shape of the other, changing its surface area, hence changing the luminosity. The gravity from one star can focus light from the first, again, changing the luminosity that we see from it. And this is actually something that happens. Alcor, which we mentioned, the partner, the companion star or the adjacent star to Mizar, the Mizar system was actually confirmed as emitting excess X-ray radiation because of the effect of a secondary. So Alcor itself is a binary system. Again, about 12 arc minutes apart from Mizar, itself a binary system of two binary systems, a visual and a spectral. Mizar is a binary, as a visual binary system, each of whose components are spectroscopic binary systems. So we see that indeed stars like to form or congregate in couples in binary systems and in hierarchical binaries, binaries of binaries. And that typically is a stable system, as opposed to triple systems, which are not stable in general. We can remind ourselves that triple systems are unstable if we look at this plot here at the bottom right, which you might remember as the effective potential from a binary system. For example, the Sun and Jupiter, a large star and a smaller star. And if you recall, there are only a few points which are actually stable for a third object close around these two. The two Lagrange points L4 and L5, which are kind of the peaks of these hills in front and behind of the line of connecting the two stars, the line of centers. There are three unstable Lagrange points, L1, N2, and L3, which are where the potential zeroes out here in between and on either side of on the line of sight, on the line of nodes, the line connecting the two stars. If you generally place a third object around such a system, it can either be bound to one of them, that's no problem. Mercury is bound to our sun. It can be bound to the smaller one, like a moon of the Earth or a moon of Jupiter, or it could be bound to both of them, but far off and not really sensing each of them separately. Or it could be in one of two very fine points in L4 or L5, like Trojan satellites and Trojan asteroids, which we mentioned in the solar system. Basically, anywhere else, it will be unstable. And so it will either fly into one, fly into the other, or most likely fly out of the system entirely. So we don't typically see triple systems. The same effect of losing a particle through Lagrange points or outside of either body is also relevant for tidal effects. Because if two stars are close enough together, they can affect each other in another way, which might be measurable, and that's through a tidal effect. So what is a tide? A tide is a differential in gravity. Gravity, as you know, is a central force. It always works towards the center of mass of the body that pulls the secondary object. For example, we can think here on the right of the Earth, and the moon will be on the right-hand side. And so the surface of the Earth and the center of the Earth and every point on the Earth is drawn or attracted gravitationally to the moon, which is on the right. And that goes like G m1, m2 over r squared. And you all know this from high school, if not from your first course in mechanics. But if this object here on the left, like the Earth, is large in extent, it has a radius, then the gravitational force will not be the same at every point on the Earth. First of all, it will be stronger on the right side because that's closer to the moon. So R is smaller, the force is larger. So if we have some average gravitational force calculated at the center of the Earth, to the right of that, we'll have a stronger force. And to the left of that, we'll have a weaker force. Another effect is direction. On the axis connecting the center of the Earth and the moon, the force is always aimed directly towards the moon, to the right. But off axis, that is above or below the axis, it's a diagonal. It's aimed at some angle towards the moon. So we have the differentials both in the right-left direction and in the up-down direction of gravity related to the moon. What this means is if you calculate the gravitational force not relative to the moon, but relative to the center of the Earth and the force that it feels, you'll find this second diagram, which shows that points to the right of the center of the Earth are effectively, relatively drawn to the right because they have a stronger force to the right than the center did. Points to the left of the center of the Earth are drawn to the right weaker than the center of the Earth. So you can consider them as having a net force which is to the left, that is in the opposite direction. Similarly, points above the center of the Earth will have a net force downwards, because that's the component of the force to the moon minus the force in the direction of right, which is the direction of the center of the Earth to the moon. And points on the bottom will have a net force towards the up direction. This is a differential force. So it's the derivative of F with respect to D, to R. And not surprisingly, the differential of 1 over R squared will be 1 over R cubed. So it's a smaller force in size, but it's a differential one. It's one that doesn't apply to the entire Earth or star homogeneously. It depends on where on the star you are. And it gives us a typical quadrupole shape. That is, it stretches one axis and it shrinks the perpendicular axis. So it squeezes the Earth in one direction and pulls it, stretches it in the perpendicular direction. And why is this called a tidal force? Because this is exactly what causes tides on Earth. The crust of the Earth, the landmass, is quite rigid, so it doesn't respond to this tidal force from the moon. But the water is not rigid. The water can flow quite easily. And so the water facing the moon or opposite the moon will rise. It will distance itself from the center of the Earth. It will go up in height. The water will rise. We call it a rising tide. The water perpendicular to the direction to the moon will sink lower down. So that's the tide running away. The water, if you stand on the shore of a lake or of the sea, you'll see the water receding. It's going elsewhere. Okay? It's going closer to the center of the Earth, which means lower in height. So this is basically the tidal effect. It's a 12-hour modulation in the height of the water, because every 12 hours, with the rotation of the Earth at 24 hours, the point of the water on the Earth will be either facing the moon or facing away from the moon. And in between of those two times, it will be low. During those times, it will be at high tide. The exact same effect happens for stars in a binary system. A star, which is circled by another star, will be stretched towards the other star. Will be squished perpendicular to the other star, stretched towards it. And it's possible that if the star is big enough and light enough, the final particle of mass at the edge of the star, when it's drawn towards the primary, will detach and be actually attracted to the other star stronger than it is to its own star. How do we calculate when this happens? So we have the tidal force of body 1 on body 2, which is this 1 over R cubed force, or large R2, which is the radius of star 2. So the radius of star 2 is the length to the edge of star 2, or the farthest away you'd be from the center, multiplied by 1 over R cubed, the separation between both stars. This gives you the tidal force on the outermost piece of mass on star number 2. The same part of star number 2, the same mass, small m, is pulled to the center of star number 2 by gm2 over r2 squared, Newton's universal gravitation. You can see that G cancels out immediately, M cancels out immediately, the actual mass doesn't matter, and you get a condition which is a ratio between m1 over r cubed to m2 over r2 cubed, or basically a relation between the density of star 2 to the effective density of star 1, that is the mass of star 1 extended to the position of the separation star 2. This means that if you have a very massive star M1, which is small enough to be close enough to star 2, it can actually have a tidal force on star 2, on the edge of star 2, which is stronger than the center of star 2 has as a gravitational pull, and it will start ripping matter off star 2. This is called tidal disruption. When star 1 actually pulls matter off of star 2. And so we separate between different types of distances of these two stars. From the previous diagram of the potentials, we identify a region of space called the rush lobe. The rush lobe is basically the region around a star, which is gravitationally bound to that star. And it reaches up until the L1 Lagrange point, where it connects to the rush lobe of the other star, the smaller star, which might be a more compact star. Smaller might actually mean heavier in this case. For example, if it's a white dwarf or a neutron star or a black hole, it will be heavier but smaller, so denser. If both stars are smaller than their rush lobes, then no matter is actually satisfying the tidal disruption criterion, and no matter is moving from star to star. So in this case, the stars are disjoint from each other. However, if the large star is thicker, for example, if it's a red giant, it can be much larger, and it can actually have its mass reach all the way to the Lagrange point. In that case, it will grow out of the region that's gravitationally bound to itself, and it will feed matter into the other star. In this case, we'll have tidal disruption, and we'll have a semi-detached binary, which is when one star feeds into the other. A contact binary is the rare case in which both stars exactly fill their rush lobes, and so they can send mass to each other, and mass can flow between both stars through the Lagrange point. And finally, if both stars overflow their rush lobes, then they can exchange mass through the Lagrange point. But what will happen is that most mass is outside of both rush lobes, which means it's no longer gravitationally bound to either of them, and it will escape out to space. This again is the instability of a three-body system. If you have a particle of mass outside this the double lobe shape, it will just fly out into space, and the system will lose mass in this way. Any questions?
Yes, the third one, the both stars fill their rush loops. Does it mean that visually, if we see that, it looks like a combined weird double star if they start feeding mass to each other?
In this, I don't think this case is so rare. You need both of them to fill exactly their rush lobes, not one of them exceeding. Mm-hmm. Actually, if one of them exceeds, then the other one will as well, because the mass on the outside will kind of flow around the other. But they need to be, well, first of all, they need to be very, very large. As we mentioned, only giant stars and supergiant stars or hypergiant stars, which are close enough to us that we can tell them as more than one pixel in an image, can actually do this. What we need here is not just to have a huge star that's close enough that we can see it geometrically, but we needed to have a companion that's also large enough and to be exactly touching it. So as far as I know, we have not yet seen visually any system like this. And it would be hard. The more common scenario is the semi-detached binary, where only one star overflows its rush lobe, transferring mass to the other smaller star, which sits in the middle of its rush lobe, not filling it. And the reason that this is a more common scenario and more easy to see scenario is that in this case, the mass flowing from the left to the right in this case will have some angular momentum coming in through the rush lobe. And since it has angular momentum and it cannot easily get rid of the angular momentum, that matter will typically accumulate in a disk around the smaller star and form an accretion disk. And that will cause matter to kind of form a disk, not a sphere, but a disk, and slowly fade in to the main star. And this accretion of matter will typically heat up the accretion disk quite a lot from friction. And it can emit X-ray and very high energy particles. And that's something that we can see. It will basically create jets of matter and beams flying out of the perpendicular to this disk. And this we can see quite well. These jets and beams of matter and radiation coming out of accretion disks. And we can see this even if we don't see the stars themselves, be it a neutron star or a black hole, we can see these jets coming off of them. Okay. Okay. Just two more slides. There is a unique case, which is interesting, which is quite common, and that's the case of a white dwarf red giant pair, or white dwarf and any other giant pair. The reason that it's common is that we said, in general, binary systems tend to form. It's easy to collapse a gas cloud into a binary system. Typically, those two objects will be of approximately the same mass. And if they're big, then they might go into a red giant or other giant phase. Eventually, they might complete their lives and large star finish their lives quite fast. And as we mentioned last week, 97% of stars in our galaxy, for example, but definitely most stars, will finish their lives as a white dwarf. And so it's quite common to find a white dwarf and other giant star companion as a bound system. In this case, the red giant might overflow its rush lobe, feed the white dwarf in an accretion disk, and the white dwarf itself doesn't do nuclear burning, but if it accretes enough matter from the red giant, then eventually the accretion disk, or feeding into the envelope or the surface of the white dwarf, can itself get hot enough, get the hydrogen hot enough to start nuclear burning. And so this white dwarf, which is the corpse of a dead star, which cannot burn hydrogen anymore, can suddenly ignite hydrogen on its surface and be born again. And that's what's called a nova, or new star. It's a giant star feeding a companion, and it's another type of a variable star, which we named the cataclysmic variable, a very dramatic, disastrous variable, where typically you have only the luminosity of the dwarf and the giant, but at some point, if the giant manages to feed the white dwarf enough, it ignites again, and you have a new significant rise in apparent magnitude. Here we see a rise from about 9 to about 2 or 1. So about 8 magnitude rise over a very, very short time of this ignition. We see that this is a matter of days for this nova to appear in the sky and then dwindle back and dim back as the hydrogen burns out. And I think this is the final slide for today. Just mentioning that we can see these nova novae, in fact, quite a lot of them. In our galaxy, we on average identify 10 a year. We think that there are about 40 a year, which we cannot see because they're blocked by dust, but we can definitely follow them. And here we see, if you look at for comparison, this trapezoid marking the position relative to this nebula, you can follow a star which is definitely changing its brightness here. This one here becomes much brighter over a period of even days or weeks. So these novae are something that we can see, and they're cataclysmic variables. We can see them on the left here as well. Relative to the rest of the photographic plate, we see that it outshines everything in its area, and then a mere month or two later, disappears back into a normal star. Okay, that's it for today. Different types of variable stars. I'm here for questions, and if not, Yehu will be here in about 10 to 15 minutes for the tutorial. Any questions?
Yes, I have two. The first one is, I think, 2 slides up. But, yes, this one. Does the mass transfers till the left one is not filling the loop anymore?
In this case, the left one is filling its rush lobe. So that's the less dense star. It doesn't matter if it's more massive or less massive, but it's less dense. Typically, it will be less massive and bigger radius. And so it reaches all the way to its rush lobe, and matter from there flows to the right to the smaller star, which is heavier. In a white dwarf red giant system, for example, the more massive star will burn out quicker. So it will finish its life as a white dwarf before the other star goes into its giant phase and dies. Then you'll have a red giant or other giant and a white dwarf companion, and the younger, lighter, larger star will feed matter into the corpse, or the older, denser, smaller, heavier star on the right.
Yeah. Well, what I asked is when does the left one stops feeding the right one? Like,
when does it stop feeding it?
Yeah, when it's getting smaller from the lobe.
Yes. So, but then you have to ask whether losing mass actually makes the star smaller or bigger.
Oh.
Because when you lose mass, you also lose gravity.
And then you expand.
So it's possible that you have to check whether it's in a stable scenario or an unstable scenario, whether it's a runaway process or whether it will actually just pass matter, finish, and then shrink back.
Okay, and so there's two options. Like, it can either keep expanding and keep feeding him matter until it gets a stable state or just fades away, or it can just shrink and become stable in the new state.
Yes.
Okay. My second question is, I get why we get the disk because of the angular momentum, but I don't get why we get the jets. Because I saw it also in like in black holes, that it emits like strong jets from the polar sides or something, and I didn't get that effect really. Why does it happen?
I think we might actually cover that when we get further down the semester, when we get to explosions and high energy phenomena.
Okay, thank you.
Okay. Any more questions? Okay. If not,